Hello everybody, my name is Ruhaan and today we will be deriving the power rule, which goes as d over dx of x to the power n is the same thing as n times x to the power n minus 1. I'm pretty sure if you guys learn calculus or are learning calculus, this is one of the most important fundamental laws. Before we get into the actual derivation of the law, I want to clear up what we need to know since we do not need to know calculus. What I mean by not knowing calculus is not knowing the chain rule or the product rule. Rather, we'll be using limits and the binomial theorem to get the answer. So basically, the thing you need to know about limit laws is that limits respect addition, as one of my teachers put it, as the limit of x to b of some function x plus some function g is the same thing as limit of x to b of f plus the limit of x to b of g. Second of all, for any polynomial function which power rule is most relevant to, limit of x as it tends to some number a of a function f is the same thing as f of a, and this is true for any polynomial with no restrictions, and that's the really important part, as if there are restrictions, this might not be true for that particular point, and you have to find the limit otherwise. Last law you need to know is that if, let's say, the limit of a function as x goes to c times k, so basically the limit of f of x as it goes to c times a constant k is the same thing as k times the limit. Because k is not being altered by x, k can simply be taken out of the limit and placed like this, and the limit will remain true. Second of all, for the binomial theorem, which if you guys are learning calculus, this is something which is included in pre-calculus, so you're already expected to know. So the theorem goes as a plus b, so any binomial to the power of n is the same as the sum of all numbers from r when it's 0 up to r when it's n. So basically what this is saying is you increase r by one succession every single time. Of n choose r, so this is combinations, and combinations as is defined here. When you see n and r written in this orientation, they're not vectors. What it says is n factorial divided by r factorial into n minus r factorial, and factorial is just, so n factorial is the same thing as n into n minus 1 into n minus 2 all the way up to 1, right? And a to the power n minus r times b to the power r. So basically the important thing is, if you guys know about binomial expansion, is that the sum of the powers is always equal to this n, and basically this is what these n minus r and r terms are doing. You start with r is equal to 0, you start with a to the power n and 1, so b becomes 1, and then you keep on going until you have b to the power n and a to the power 0, so you have b to the power n. And that's basically most of the things you need to know. And of course you guys need to know that a derivative of a function can be defined as a limit with this notation as d over dx of f of x. So the derivative of f of x is the limit as some delta x tends to 0, where the delta x is incorporated into the function as such. Now this would make more sense on the next page. So when we set up a problem here, we see the limit basically acting up. So we have a function, some x to the power n. It does look like e to the power x, or some constant to the power x, but that's not really important. I just tried to make it as clear as possible. But what I'm trying to say is that let's assume this is some portion of a function as of x to the power n. It could be a parabola, right, for example. And what we're doing is we choose any 2 points, and we take a difference between those points, and that's delta x. So, and this is that particular difference. So you have 0.1 and you have 0.1 plus delta x. So you go by that difference over to that side, and then you have corresponding values of y. And as you know from basic algebra and basic function notation, as we did even with straight lines, the gradient of a line is just your change in y divided by change in x. And because we want to find the instantaneous rate of change, which is described by this red tangent of the curve here, is what we want to do is we want to reduce this down all the way up to 0. So we have a tangent to a singular point on the function, which gives us the instantaneous rate of change. therefore the derivative. So here I've set up the simple equation which we need to follow. We need to take the first derivative of f such that f of x is equal to x to the power n. So by just general knowledge of the limit laws, we can say that limit as dx tends to 0 of f of x plus dx minus f of x divided by dx. Further expanding this, we can write this as limit of dx tends to 0 of divided by delta x. Now what I'm going to do is I'm going to quickly rewrite this as limit L over dx. So basically what I've done here is I've actually denoted the top part as L. So now we can start evaluating and simplifying the top without having to rewrite the definition of a limit over and over again. So let's do that, right? So we have L, and now L is equal to x plus dx to the power of n. We learned from the binomial theorem that you can simply rewrite this as the sum of some number r as it goes from 0 to n. You write the combination n, choose r, and it's x to the power n minus r, and dx, which I'm going to put into brackets, to the power r. And then we simply subtract x to the power n. Now the next thing we need to do is we need to observe the fact that for this binomial expansion, the first term would be x to the power n, and I'll simply prove that to you later. But recognizing that fact, you can already see that this number can easily be cancelled, and then we're left with just a summation, which we can further simplify, right? So let's do that, right? Let's take out r as it's equal to 0. So we have n, choose 0, times x to the power n minus 0 times dx all to the power of 0. And then what you have done is this is a summation. So if you have taken one out, the summation therefore starts with r is equal to 1, because this is r is equal to 0 all the way up to. Also, please feel free to pause the video at any time if you want to just confirm whether these calculations are correct. Now, from the previous formula, instead of writing equal to, I'm just going to solve this like this. So from the previous formula, we know that n factorial and 0 factorial times n minus 0 factorial would equal, so 0 factorial is equal to 1, right? So this is basically equal to n factorial divided by 1 into n factorial, which can further be cancelled out, so you're left with 1. So this becomes equal to 1. You know, anything a to the power 0 must always be 1. So this is also equal to 1. So we're left with a simple statement that x to the power n minus x to the power n plus. Now using this, we can just eliminate this, and we have a new limit, a new summation for the value of L. So again, here what I want you guys to think about is the fact that what happens if we divide this by dx, right? At this current stage, because it's a summation, right? So we can take the dx is in every single term, and it's a product. So, you know, this is implicitly being multiplied, and this is also being multiplied. So therefore, if we have a bunch of terms, and they all are products and they're being summed to each other, we can basically take this out as a common factor. And right now, if we divide this term by dx, if we do dx to the power r to the power of r divided by dx, we get the simple expression dx to the power r minus 1. Now, plugging r minus 1 back into the summation, you notice something very important. So if this becomes r minus 1, right? If we think for a second, this becomes r minus 1. The first term of this particular summation would result in dx to the power 1 minus 1, which is equal to dx to the power 0, which is equal to 1. Therefore, for that one particular term, we would be left with this particular expression. Let's call it f. We'd be left with a simple thing like this. And when we take the limit to 0, we'll just get the answer that if dx tends to 0 of f over dx that will just give us infinity or plus or minus. I can't really say without looking at the function, right? So this gives us a clue that maybe we need to do another sort of excursion here. So by excursion, I mean, you know what, let's experiment and let's take out this r is equal to 1 aspect. Now we have done that before and we'll do that again. So let's take r is equal to 1. This is the value for r is equal to 1. Therefore, we need to add r is equal to 2 up to n for the remaining terms. So now let's simplify. So this can be rewritten as n factorial, 1 factorial, and n minus 1 factorial, which is going to give us n. And that's mainly because if you expand this, so if we write n factorial is equal to n into n minus 1 into n minus 2 all the way up to 1, we're basically saying that n factorial is equal to n into n minus 1 factorial. So therefore we can cancel this out with this and we're just left with the value n. So we know that L is equal to n multiplied by x to the power n minus 1 times some delta x. So here now we have an expression for L. And this is our final value of L. And how do I know we can simplify this? You know, that might be a question of yours. Well, if you do the same exercise, but for the new thing. So now if r minus 1 is plugged into this, right? If r minus 1 is plugged into this, the first term will also contain dx. So we can actually cancel that out with the denominator, and that's something which is going to be done. So now let's take these two things we learned and let's apply them together. Let's go to a new page. I'm going to restate our two equations. So equation 1 and our second equation is that L is equal to n times x to the power n minus 1 delta x. So here we have two equations. Before we continue on with the proof and actually get the final power law, one thing I would like to clarify as one flaw of this proof without using calculus is the simple fact that what we're doing here is we're proving the power law true for all numbers n, which are integers. So this could be negative or positive integers, including 0. However, this does not include fractions. Now let's combine these two particular equations. So we have f of x is equal to the limit of delta x to 0 of this L. So I'm just going to write that again, which now using the limit laws that we learned, we can actually separate this. So first what I'm going to do is I'm going to quickly write this as limit dx tends to 0 of n times x to the power n minus 1 dx to the power dx. So basically I'm separating these addition terms. We have limit. Now first let's evaluate this particular limit. So what I'm going to do is I'm going to write an equation equal to sign here in vertical format. So what we're seeing here is that because this is a summation, right? So this is, you have some constant, and you have x to the power. So what we have here is some constant k, x to the power n minus 2, dx to the power 2, and then plus a lot of these numbers until we get to dx to the power n, right? And when we divide this by dx, what we're doing is we're subtracting 1 from every single power. We're taking a common factor out of dx, and what we're doing is this. We're subtracting 1 from every single power, and that you can just simply see using the power, right? We took out the factor, so we write it as this. And we're doing that with all of the terms as it goes from 2 to n, right? And one thing you can do is then when you take the limit, all of these dx's are non-zeros, right? Non-zero. So they're non-zero, which means is that whenever, as we take the limit to dx is equal to 0, all of this would equate to 0. Now let's look here, right? So before we take the limit, we of course have to take the dx out of the denominator. And what we can do is simply n times x to the power n minus 1 times dx over dx, because they're all in multiplication, which just simply gives us n times x to the power n minus 1. And because we know the factor rule, we can just take this out of the limit and it equals to itself. There's no limit taking here. So using now this new developed limit, we can just say that d of dx of x to the power n is simply equal to the non-zero solution. It's equal to nx power n minus 1.
And here you have a proof for the power law without actually using calculus. Thank you very much to everyone for watching this video. Thank you very much for supporting the channel. If you liked the video, please make sure to drop a like and subscribe if you want to see similar content. It's been a pleasure, and I hope you learned something new. Thank you very much. See you guys.